Okay. Let me, my cursor is. Okay, there we go.
Hi,
Okay.
everyone. Thanks for coming today. We have Emma from Berkeley as our speaker. She's going to talk about her recent work of private TimeSeries database from Malicious Security. Let's welcome her.
Thanks so much for having me. It's great to be here in person. Much better than all these virtual talks. So yeah, great to be here. Yeah, so I'm going to be talking today, as Chris said, about a private TimeSeries database from function secret sharing. This is joint work with my co-authors, Mayank, Raluca, and Ion at UC Berkeley, and appeared this last spring at Oakland. Ooh, can't advance my slides. Just a second. Just gonna try to. 1 second. Okay, there we go. Not sure what happened. Okay, so TimeSeries data. So there's a growing trend of relying on cloud databases to store and query TimeSeries data. So examples of this include smart homes, industrial IoT, and remote patient monitoring. One challenge with all these applications is that the data is often sensitive. And so there's a real danger of server compromise. So to make this a bit more concrete, let's consider the example of remote patient monitoring. So we have some patient and we have some database, and this database has fields like timestamp, systolic, diastolic blood pressure, and a heart rate. And over time, the patient is going to send records to the database, going to populate this table. And then at some later point, we're going to have some doctor that wants to make some query about the patient's data. So let's say, for example, they want to compute the average heart rate over some time interval where the systolic blood pressure is greater than 110 or the diastolic blood pressure is greater than 80. So they want to compute some aggregate query based on some multi-predicate filter. Now we're also concerned about some attacker that can break into the database, and we'd like to protect the data contents as well as the query filter values in this case. So the contents of the table, and then also the query filter values are these values in the predicate. So the time interval that we're considering, as well as the systolic blood pressure value 110 and diastolic blood pressure value 80. So we'd like to protect all of these from the attacker. So there's been a lot of prior work on encrypted databases, looking at how we can protect both the data contents as well as the query. One challenge with all of this prior work is that a lot of it has leakage. So there's some trade-off between the information that the attacker learns in order to achieve more efficiency. And this leakage can often be exploited to allow the attacker to learn information so it can recover the data and or the query. So there's a lot of these statistical attacks that can leverage this leakage to learn information that you'd like to keep private. And so our goal is to protect search access patterns. So importantly, how the server accesses data shouldn't reveal information about the data or the query results. So we want to be accessing this data obliviously, and how we access the data shouldn't reveal private information. So one challenge in finding a solution is that generic tools for hiding search access patterns are expensive in the TimeSeries setting. So for example, you might consider an ORAM-based solution or an MPC-based solution. TimeSeries workloads tend to be append heavy, and these queries are multidimensional. And so these tools can be expensive when you're trying to just run these applications using these sort of generic tools. So we'd like to achieve these sort of 3 goals. So functionality, so multi-predicate aggregation queries, efficiency, so we'd like to minimize latency and communication, while also protecting the data contents, query filter values, and search access patterns. And so our system, Waldo, is going to achieve all 3 of these simultaneously. Also, feel free to interrupt me for questions. Yeah. That's a great question. I don't have a fantastic answer. We liked the name. Waldo also, cares about privacy. He likes to stay hidden. And I wish I had a better answer beyond that. We liked it. Yeah. Yeah, feel free to interrupt me for all sorts of questions. Okay, so we're going to consider the following threat model. So we're going to assume 3 servers, and these servers are going to be deployed in different trust domains. And then we're going to have a bunch of clients interacting with these servers. So if we're considering the remote patient monitoring setting, some of these might be patients that are uploading their data, and others might be doctors that are querying the data. So we're going to consider the case where we have at most one malicious compromise. So we're going to be in the three-party on its majority setting. And in this setting, Waldo is going to protect the data contents as well as query filter values and search access patterns. So we're not going to reveal the contents of these tables as well as the query filter values, and how the server accesses data isn't going to reveal this private information. And the server is going to be allowed to learn the database schema, so how the data is laid out, as well as the structure of the query. This is a little bit abstract. To make this more concrete, let's go back to the original example that I showed before, where the patient's making a bunch of queries. We have all these fields, time, systolic, diastolic, blood pressure, heart rate. So Waldo is going to hide the contents of these fields. So each of the fields, we're just going to have some opaque identifier associated with each field. So here, F1, F2, F3, F4. And we're not going to reveal the contents of that data. And the attacker is just going to learn that the doctor's query is of the form computing the average, where F1 is in some interval, and F2 is greater than some value, or F3 is greater than some different value. Also, we're going to protect search access patterns. So how the server is accessing data isn't going to reveal any private information. Any questions about this? Okay, cool. Okay, so for the rest of the talk, I'm going to start off with a simple strawman. So we're going to have a simple solution with just two servers that operates on public data, and we're just going to have single predicates, and it's going to achieve semi-honest security. So the adversary can only observe execution. And then over time, we'll build up to our solution that uses 3 servers and is going to operate on private data, combine multiple predicates, and then achieve malicious security. So the adversary can arbitrarily influence execution.
So in a strawman, you're not protecting the data first.
Correct, correct. And I'll show how we get that.
Right.
Yeah. Simpler to show sort of one step at a time. So just simple notation, secret sharing some value X in the ring 2 of the L, split into secret shares X1 through Xn, sum them together, get the original value X. So we identify function secret sharing as being particularly well suited for the setting of time series data. So in function secret sharing, if you have a 2-party function secret sharing scheme for a function F, you can split it into 2 succinct shares. You can call these shares keys, such that given a key, parties can compute shares of the function F evaluated at X without learning the original function F. So given just one of these keys, I can compute a share of the function F evaluated at X without knowing what F is. So to make this a bit more concrete, we can consider the following syntax. So we have some gen function that's going to take as input this function F, and it's going to generate keys K1 and K2, such that one of these keys individually is going to hide the function F. So only if you have both of these keys can you actually learn the original function. There's also some eval routine where given some key K and some input X, we can output shares of the function evaluated at point X. So if we sum together the evaluation of key K1 at X with the evaluation of key K2 at X, we'll get the function F evaluated at X. And efficient constructions exist for point functions as well as comparison functions. So functions that are going to be a particular value at a single point and 0 everywhere else. And also functions that are going to be a particular value at a point greater, at all the points greater than some value and 0 everywhere else. Okay, so now we can leverage function secret sharing to build aggregation queries for public data in a pretty straightforward way. So we're going to start off with 2 servers. And let's say the doctor wants to compute the sum of all the medical costs for patient with ID 112. And here we're going to hide that the patient ID is 112. Okay, so and the 2 servers are going to have identical copies of this table with the patient ID and the cost in each row. So the doctor is going to start off by generating FSS keys for the function that evaluates to 1 at point 112. Just going to use this informal syntax here for this function for the rest of this talk. So we're going to send key K1 to the first server and key K2 to the second server. And now for each of the rows, we're going to evaluate the key at the ID in that row and then multiply it by the cost. So here we're selecting patient ID with 112. That's going to evaluate to be a share of 1. We multiply that by the cost, we get shares of 1,000. Do this for the next row. This time going to evaluate to be shares of 0. So multiply and get shares of 0. Next row, so evaluate to be shares of 1, multiply that together. Then we sum all these up. And then we send back shares of the final answer, which is 1,700. The doctor can sum these together and then output the result of the query. So in this way, we built aggregate queries for public data in a fairly straightforward way. The challenge here is how do we extend these techniques to private data? So in function secret sharing, you need to pass the input directly to this eval routine. But in this case, we'd like to hide what the patient ID is from the server. Patient ID may be not a super sensitive field, but you could imagine wanting to query on other fields that are more sensitive. And in that case, we'd like to actually keep this information private from the server. And we don't want to, and the problem is that we need to provide this value directly to this eval routine. So how can we get around this and actually use function secret sharing to query private data? So our idea here is to leverage the structure of the search index itself. So we're going to construct a table for each feature where we have, for each column, we have a record. And for each row, we're going to have one possible value of that feature. I'll explain why we can consider that these features are from a relatively small domain in just a second. And so each column is essentially going to be a one-hot encoding of that feature. So here, entry I, j is going to equal 1 if record j is heart rate I and 0 otherwise. So here we can see record 3 is heart rate 79 because row 79, column 3 is set to 1, and that column is 0 everywhere else.
What happens if the data is like continuous?
So we're really only considering discrete values that we want to do predicates on. You can also bucket these values. So for most applications, you only care up to some precision for filtering. So it's application specific how you might handle it. Yeah. Okay, so appends are also cheap in this setting. So if you're just appending a value, as we often do in time series, we care only about appends, not updates. You can just add a column to this table. And we're really only targeting applications that are querying recent data. So we can constrain the size of this table, just consider a window and throw out older columns as they're no longer necessary. So we only care about querying relatively recent data. And this is true for most time series applications. So one limitation, I alluded to this earlier, is that now the domain of our filtered features is constrained because we need a row for every possible value. However, in the applications we examined, we found that features and predicates were already from a fairly small domain or could easily be mapped to one. So for example, around 256. These include age, height, heart rate, blood glucose level, or some percentage. You can also represent large domains via conjunction. So you can have a feature for the high order bits and a feature for a low order bits, and then consider some and between the two. And also this is only going to restrict features that you're filtering on, not features that you're aggregating. Okay, so now I'm going to show how we can actually leverage that search index structure in order to search on private data. So now each server is going to have a copy of this table. Let's assume for now we have some way to protect the contents of the table in gray. I'm going to show you how we do that in just a second, but just assume it's protected for now. So let's say the doctor wants to compute the number of records where the heart rate is equal to 80. So as before, we're going to compute the FSS keys for the function that evaluates to 1 at 80 and 0 everywhere else. We're going to send a key to each of the servers. And now what we're going to do is for each row, we'll evaluate the key on the value corresponding to that row. So evaluate key K1 at server 1 on 79, and then multiply that evaluation by each of the values in the row, and then sum them all together. So here, the evaluation of the key at 79 is just going to be shares of 0. So this row will just evaluate to be a share of 0. We'll do the same thing for the next row. This time we'll get shares of 1, multiply that by each of the values in the row, sum them together and get shares of 2, and so on. Sum all this together, send back, we get shares of 2. This is the number of records where the heart rate is equal to 80. Then we can sum these together and we'll output the result, which here is just 2. So here we're still assuming that we have some way of protecting the structure, the contents of this table in gray. I'll show how we do that in just a second. Any questions before I move on?
Why can't you just have detail for the data object?
Yeah. So the challenge is I'm going to show how we protect this in just a second. But the concern is that the server needs to pass the input directly into this eval function, so it can't pass in like a ciphertext or a secret share or something like that to get the right output. That's the challenge that we're trying to solve here. This is sort of part 1 of the solution. I'll show you part 2 in 1 second. Yeah. Okay. So now how do we actually protect the contents of this table in gray? So we need to make sure that the values sum together correctly. So these function secret sharing keys are going to give you these shares of some value beta. You have some secret at the servers. If it's just given to both servers, you multiply shares of beta times some value S, and then the doctor can sum these together to easily get beta times S. The challenge is, how do we actually protect this value S? So some first attempt could be using additively homomorphic encryption. Challenge here is that public key operations are expensive. We would need to do a public key operation for the number of records times the number, or times the domain of our feature. So that's going to get expensive. We could also consider just having these as secret shares. The challenge now here, multiplying secret shares together is expensive. If you want to, get an answer that actually makes sense. And so you would need communication linear in the number of records times the feature size, which we would like to avoid. So what we do instead is notice that replicated secret sharing is particularly well suited for function secret sharing. So this is why we introduced the third server. So now we're going to split the contents of the table, so the stuff in gray, into 3 shares. So if you sum each bit of the table together from share 1, share 2, and share 3, you'll get the contents of the original table. And we're going to give shares 1 and 2 to the first server, shares 2 and 3 to the second server, and shares 3 and 1 to the third server. So now we're going to essentially run the same protocol as before on each of the shares of the table. So now instead of generating 1 pair of keys, the doctor is going to generate 3 pairs of keys. And it's going to give keys to the servers corresponding to the shares of the table that they have. So now the servers are going to first run the protocol on share 1 of the table, and then on share 2 of the table, finally on share 3 of the table. They send the results back. And now the servers just need to add together all these results computed on the different shares of the table to get back the same thing they would get if they executed this query on just the plain text copy of this table.
So the share at the table is like 3 out of 3, and the share of the function key is 2 out of 3.
Yeah. Any other questions? Okay. Cool. Yeah, and there's some similar ideas that are used in the distributed ORAM settings. There's some work from Fun et al. That also notices that RSS and function secret sharing are well suited. This is more in the distributed ORAM setting where you just care about reading and writing data. Here we're looking at more complex queries, but just worth noting that there's a connection there. Okay, so I want to move on to talking about our second challenge, so how we support multiple predicates. So let's say now we want to compute the number of records where the heart rate is equal to 80 and the age is equal to 24. A little bit of a contrived query, but shows what we need to do here. So let's say, just as before, we have these tables for the heart rate values. So just as before, we're going to send the keys for this predicate to the servers. And now when we evaluate the values, instead of summing across all the columns to get one single value, we're just going to sum within one column. Within each of these columns. And this is going to allow us to get secret shares of some vector that's going to be 1 if the record matches the filter and 0 if the record doesn't match the filter. So here we're essentially obliviously selecting all the records where the heart rate is equal to 80. Now we can do the same thing for the second part of the predicate. So we're going to send these keys for the age is equal to 24 query. Going to run the query and get shares of the bit vector that's going to be 1 for the records where the age is equal to 24 and 0 everywhere else. So now we have shares of these 2 filters. We just need to add them together now in order to get shares of the filter that represents both of these predicates, so the full query. So adding them together, just multiplication, and we can use techniques that already exist for secure multiplication for replicated secret sharing to do this. That's going to allow us to get the filter for both of these predicates. And if we're computing count, we can just sum all these values together. Sum, you have to do some multiplication before you sum together. Okay, so I want to move on to our third challenge now. So malicious security. So up to this point, we've only been considering a semi-honest adversary. So the adversary can just observe execution, but can't actually influence the server's behavior. We'd also like to defend against the stronger notion of malicious security. So one way to do this would be using information theoretic max or operating in rings, so techniques from Speeds 2K. So a first attempt would be to keep a MAC tag for every entry in the index. So here we could have a doctor who's making queries. They're going to have some MAC key alpha. And now the servers, instead of just storing RSS shares of the values X, they're also going to store shares of alpha times X. These will be the MAC tags. The server will send some query. They'll run the query on both the X and the alpha times X shares. And then we'll send back values. We're going to get a result and a tag value sigma, and then check that the result, so alpha times Y is going to be equal to our MAC tag sigma. This is a straightforward way to use MACs here to get malicious security. The challenge with this solution is that it results in large storage overhead. So now for each value, you also need to store the corresponding MAC tag. So you're actually more than doubling the amount of storage you need, since these MACs also need to be larger. And also user revocation is challenging. So let's say Alice and Bob both had access to this database, and now Alice wants to revoke Bob's access. She's going to need to recompute fresh MAC tags for everything. Not super feasible for most applications where you do actually care about changing membership fairly frequently. Okay, so our idea is to actually encode the MAC key directly in the FSS key itself. So instead of just generating one FSS key pair or one logical FSS key pair, I'm just going to show this for one pair of servers. You would actually repeat this for all 3 pairs of servers. Just makes the arrows a little bit simpler. So now the doctor is going to choose some random alpha value. So it's MAC key. This is going to be random for each query. Then it's going to generate 2 pairs of keys now. So one that's going to evaluate at 1 at the point X, and then another that's going to evaluate to alpha at the point X. So the random per query MAC key. It's going to send the first key from each of these key pairs to the first server, and then the second key from both of these key pairs to the second server. We'll evaluate and send back the results Y corresponding to the first key, and then the shares of the sigma value corresponding to the second key pair. And then we can reconstruct and check that alpha times Y is equal to sigma. So we're essentially doing the same thing as before, but now instead of needing to actually store the MAC tags at the server, we're encoding it directly in the key. And this is going to make it much easier because now we don't need to store extra stuff. And also it's easier to revoke users because you don't have to worry about needing to rekey everything in the database. So both these points that I just said on the slide. So Boyle et al. Proposed something similar for the MPC setting, where you have a bunch of different parties and then you do some joint verification. The setting is a little bit different because the client can verify the MAC tag directly, since we're in this client server setting, but similar techniques apply here as well. Okay. So just to summarize the queries that we support, I've gone over a bunch of techniques. So we can support equality and range predicates. So I've shown mostly just equality predicates so far, but there are also FSS constructions for range queries. And these are going to map pretty directly to range predicates. We can chain together Boolean operations for and, or, and not, and support aggregation queries for sum, count, mean, variance, and standard deviation. For some of these, the client is actually going to learn some intermediate values. So for example, for mean, the client learns sum and count. And additional rounds can be used to support nesting, so where the aggregate's actually used as a query filter value. And with that, we can support these more general queries, like this query for congestive heart failure risk. Okay, I'm going to talk, oh yeah, and then there's another construction that I don't have time to talk about in detail, but just want to mention that it's there in the paper if you're curious. So far we've just talked about linear aggregation functions, but for some applications you might care about nonlinear aggregation functions like max, min, or top k. And so we show a tree-based construction that allows you to do this without leaking a bunch of extra stuff, just at a very informal level. The downside is that you can only filter on time, and so you can't do these fancy multi-predicate filtering techniques. But this will actually hide the data contents as well as the queried time interval. And you can do this all using a single logical FSS key, and it doesn't require interaction between the servers.
Oh, what do you mean by fancy?
Oh, you can only filter based on time, and so you can't filter based on other features. So I've been showing queries largely where you can filter on things like patient ID and heart rate and blood glucose level and all sorts of fancy things. Here, it's just saying I want to compute like the max over some time range or top k within some time range. So it's more limited in one setting, and that you can only filter based on time, but more expressive in terms of the functions that it can support. Yeah. Okay. So now I want to move on to talking about evaluation. So the code is available, open sourced. So we run experiments with 3 32-core servers configured with a 3 GB per second connection and a 20 millisecond round trip time. And we do all our queries that I'm going to show with eight predicate queries. We consider 2 baselines. So an oblivious multi-dimensional tree. So we run an R tree inside of path ORAM. And we also consider a generic MPC baseline. So we run MP speeds in the 3-party honest majority setting. Okay, so here we're looking at latency from around 1,000 records to around 1 million. For our solution, point and range perform almost identically. So they look like almost one line. And we can see for around 1,000 records, there's about an 8x difference between us and the MPC baseline, and around a 37x difference between us and the ORAM baseline. And then over time, the performance for both us and MPC is going to grow linearly with n, whereas the ORAM baseline is growing polylogarithmically. So this gap is starting to close. This is a log-log plot, so the gap looks smaller than it actually is. But there is going to be some point where an ORAM-based solution is going to be better if you're just considering purely latency.
So what's the range of data you're considering?
Range in, oh, we're considering a feature size of around 256.
Oh.
Yeah. Yeah.
256.
For the feature size.
Oh, right.
Yeah. Since that, for most of the applications we looked at, we found that was reasonable to express what you cared about. Yeah.
So basically have a constant of 256.
Yeah, exactly. So it's linear in the number of records times the feature size. There's, the 256 thrown in. And so there is going to be a point if you care about a really large number of records where ORAM is going to be better in terms of query latency. But for most of the applications that we found, you're not querying over, necessarily a really large number of records. Or, if you have a lot of records, you can sort of aggregate them together and then, and then query over them. So there will be a point at which ORAM is better, but for the applications we found, this works pretty well. Yeah.
Difference between the point and range.
Oh, so this is where the predicates, so the point one is where the predicates are all point queries. So just x is equal to some alpha, and range is just x is greater than alpha. These perform really identically because the cost for these different types of FSS functions almost identical. So you don't really see the difference here. It's just included for completeness, but the other line is, the way I plotted it, they're just on top of each other. Yeah.
I was trying to find the base.
You're really lucky. Yeah. It's hiding behind the dark blue line. Yeah. Yes. Yep. Good question. Yeah. Okay. So throughput is where you can really see the gap between Waldo and ORAM. So I mentioned earlier that these time series workloads tend to be append intensive. So here we're considering a workload that's 90% appends and 10% queries. In many workloads, it's maybe even closer to like 99% and 1%. And here we can see the gap is much larger because in ORAM, you have to do a bunch of these tree operations that are now done inside of ORAM to do the updates. Whereas in Waldo, you're just appending a column and you don't even have to do that obliviously. So there's around a 300x difference in throughput for around 1,000 records and a 22x difference in throughput for around 1 million records. And this is really just due to the overhead of these appends in ORAM. And so we can really see the benefits of when you have an append-intensive workload of only incurring the cost of this obliviousness for the queries and not the appends.
Is there a
Yeah.
one expression to show that the complexity of one query? Because there's not one in this one.
Yeah. So it's going to be the number of records times the feature size, and then you're also going to incur some costs for replication due to RSS, and then an additional 2x for the malicious security. Yeah, so number of records times feature size, then times 3, and times 2, basically.
Okay.
Yeah.
So it's only going to be like some secret sharing operation. So it's going to be like some adding very basic. Yeah. So when you have multiple predicates, you're going to incur this computational cost for each of the predicates, and then when you and them together, you're going to incur communication costs linear in the number of records, but not linear in the number of records times the feature size. So you make sure that you don't have, so that's not a factor in the communication. Oh,
yeah. Okay. So in conclusion, we provide a time series database that provides functionality, security, and efficiency. So we support multi-predicate queries while hiding the data contents, query filter values, and search access patterns. And we achieve low latency, high throughput, and low bandwidth. And happy to take any questions.
Here, the access pattern is simply this, you enumerate the whole data.
Yeah, because you're touching every record in the database, you're not going to leak anything. Yeah. So similar to PIR in that sense. Yeah.
There's no reason why, like, you're paranoid, you can't scale this up to more servers using the same thought process, right?
So you could, and you could probably repeat this. I would need to think, like, if you did like 4 servers, how this would work with like replicated secret sharing. But I think with some, I think it wouldn't require much work to do this with more servers. Yeah. It's not clear that you necessarily get. We need to think a little more if you get something beyond, like, if you scale the 4 servers, if you had like if you actually got like 2 out of 4 instead of 3 out of 4, if you would get more meaningful security guarantees. But yeah, there's probably potential to scale up. Yeah, I just haven't thought through it.
How do you envision the appends to work? Like, would they need to run some sort of like consensus protocol or something to? Yeah.
So one thing you could do, so some prior work that we did, Dory looks at how you manage consensus in these sort of encrypted search style settings where you have updates and then you have multiple servers that are processing the queries. So you could imagine doing a similar solution there where you have the updates are essentially going to like one of these replicas that's going to ensure some ordering, and then you're going to switch over to the next. So you'll collect updates in some batch and then switch over to the next version periodically and make sure that both servers just agree on which batch you're on. Because you're right, you do need to make sure that both the servers are executing the query on identical copies of this database, otherwise you're going to be in trouble. And if there's some ordering problems, you end up with issues. But you can apply existing techniques in a fairly black box way. Does that answer your question? Yeah, okay.
So in the application, the 3 servers has identical copies of the data. What if they just each have part of the data?
So here they do actually have different copies of the data, right? So they're going to have replicated secret shares. So server 1 is going to have sort of shares 1 and 2, server 2 shares 2 and 3, and server 3 shares 3 and 1. So it is going to be a little bit different, but they're going to have shares of like the same thing.
Did you look at trying to sort of compress the keys to only sort of set in 1 key instead of like 8? Because I guess right now you sort of have to do sort of like 8 mirror scans or something, right? Because you have to do 1 mirror scan per key.
Yeah. So you can group together the scans that you're basically, so the cost of scanning over in terms of memory is amortized, but you're still doing the computational cost of the evaluation per key. I think if we had if there was a better solution for RSS based DPF constructions, I think there might actually have, since we published the paper, been something about this, but not sure that for our setting that it actually improves the concrete cost. But you basically needed a DPF construction for RSS shares that was better than just doing this 3 and then give 2 to each.
I think the more interesting question here is to get rid of the limitation on future value. Yeah, that is probably the main limitation, is the fact that this does scale with a feature size. And for the applications that we considered, this was a reasonable trade-off, but this does mean that we're more limited to the applications where this actually holds.
But in the sort of like database setting, like the data value needs to be input into the DPF, right? So that's like why you have to do the
Yes.
So I don't know if there's a way to get around that.
Yeah. Using this technique, so it seems hard if you're using DPFs in a black box way. But yeah, interesting direction for future work if there's a way around that.
Did you look at the homomorphic secret sharing direction? Because like that probably lets you do it.
Yeah. That could probably improve that. Most of those constructions aren't super practical at this point. And so that was why we went with more of the FSS line of work. But could be an interesting theoretical line of work, or if these constructions get better. Definitely interesting. Yeah.
Do you compute the query with the tags every time you query it, or just once every now and then to verify?
Yeah, we currently do it every time so that the client always makes sure that it gets the right value. But you could imagine that maybe if you were in some, if you were some big organization and you were you could imagine maybe periodically doing this every now and then to just sort of make sure things were done correctly. We obviously get weaker guarantees and could hope that, the adversary, wasn't only messing up a few very important queries. But maybe that's good enough for some applications. Yeah. A good question.
Let's take Emma again.